So when thinking about transparency, it really poses the question, what does that mean? We often get asked to build with glass, and that always the transparency question comes up. So what is transparency? And for me, this is one of the very good examples. Although this is a concrete building, the glass in this building is so transparent that it allows you this connection, the view out, connection with nature, and you really don't see anything in the area where there is a window. So bit more of a glassy building. This is the old Terminal 6 at JFK, iron paste design, which really brings a wall to nothing. It really very nicely distorts the relationship between inside and outside. And that hasn't always been the case, but the idea has always been there. When we're looking at the very old greenhouse structures, the Victorian greenhouses, initially the idea was primarily to bring light in, to grow plants, and that started off with solid walls that had windows in them and then bringing a glass roof on top. But it quickly evolved through iterations, not of the same building, but of various buildings to iron structures that were stiffened with glass. And whilst at the time, when they were built, that wasn't done consciously necessarily, so it wasn't really known. The glass was used to brace these very slender iron structures. So this can really be seen, even if not done on purpose, as the first use of structural glass. And then from there on, through the last 150 years, we've really seen an increase in transparent structures and an increase of structural use of glass. To understand, though, what makes these buildings appear transparent, it is very important to go back and look at what is transparency actually. So when we do that with glass, transparency really, very simply, is just the physical property of transmitting light through a material. And whilst glass does a lot of that, there's always a small portion that isn't transmitted but is reflected and absorbed. And both the reflection and absorption are important. The absorption because that has an effect on the appearance of color. And when we look at color, it really plays in the architectural use of glass a very important role. Looking at these images from left to right are 12 millimeter layers of low iron glass stacked up. On the left we see 2 layers with a light transmittance of 88%, whilst then in the middle 5 layers look a little bit more colored already, and then on the very right a cube made out of 20 layers of laminated glass, really the color becomes very evident, and seeing through that the image that is seen on the outside gets distorted through that color. And really the question comes up whether transparency is the right word. Should we be talking rather about clarity or neutrality when talking about transparency in an architectural sense? Peter Rice had put together 2 definitions of transparency, which I think are very useful. The first one he defined as one-way transparency, and that is really what is shown in this image, is just the idea of light coming into a building. So whilst you might have a very light-flooded room, there are no windows that allow a view out. So the building is transmitting light, but it doesn't allow anybody inside to see out. And that is really how we define transparency these days in a modern way. It allows light to come into the building, but also it allows a view out. And Peter Rice at the time defined that as two-way transparency, and that is really what makes glass magical. It is what makes glass this magical material. It allows to provide a protection layer around somebody in a building, but still it provides that connection between inside and outside. So why is that? Why is it possible to see through the glass from the inside to the outside? This has to do, to an extent, with the light levels and with the reflectivity of the glass. So when we have very high light levels on the outside of a building, a lot of light gets reflected. So if we're standing on the outside of a building, often what happens is that we don't find glass buildings to appear very transparent from the outside. They are rather reflective or dark. So why is that? A lot of the light on the outside, very high light levels compared to internal light levels being very low, which usually is the case because we can't achieve as high light in a building than the sun does. So light is reflected back, and we see that surface as being black and reflective, whereas when we're on the inside, the light on the outside really allows us to see through from the inside. And here's two examples that show that very well. A glass panel seen from the outside with very high light levels being quite reflective and looking quite dark, whereas when on the right side, you're on the inside of a building, you really see that magic happen that glass can do, where there's a merge of inside and outside, and nature really comes into the building. So the only thing you can see here is not really the glass, it's just the floor grill. So whilst that is a really important to understand, often we just see the request for transparency when we're looking at projects. And before we go into the projects that are ideas, sometimes what happens is that real projects get revisited. And an example all of you know is the Apple Cube in New York, but it's a very nice example because it shows how transparency can be increased. So we're not going to dwell on this, but the building was developed at the time with the technology available, which typically used to be the case for glass structures. Whenever people design with glass, it seems to be to the edge of what is possible in the industry. So the building was very transparent, or deemed very transparent at the time. Whilst after it was built, the industry had moved on and larger panels became available, the client had decided to revisit the structure and rebuild it with what was available 5 years later. So panels became much bigger, and we see a significant increase in transparency. When looking at the original structure, what becomes very evident is that the connections are what makes the structure appear less transparent, perhaps. And it isn't only the connections, though, but it's also the glass edges. So the light, again, that reflects on the glass edge really becomes very visible. So in the revisited structure, that is much less visible just because there are less edges available that the light can reflect on. But still here, really, the connections and the edges are still quite apparent. Whilst it doesn't happen that often that we rebuild the same structure twice, it does happen reasonably often that people think about doing that and revisiting the way that a structure is made when it becomes older and it needs refurbishing. So at that point, I'm going to hand over to Gregor, who's going to walk us through a couple of projects that we've been thinking about revisiting.
So this is a project in San Francisco, which is probably a painful reminder to some of you in the audience that were involved with it. There are many people here at the conference that worked very hard on this project, and ultimately, due to an owner decision, it just didn't end up getting built. But it's a very interesting project nonetheless. So in downtown San Francisco, there's a tower designed by Philip Johnson in 1982, so about 37 years ago. And at the base of that tower is a glass entry vestibule. And Philip Johnson envisioned this to be as transparent as possible, primarily because it's located underneath a tower where, there's a lot of, it's already in the shadow of the building. And so his vision for this was to be as transparent as possible. And to give you guys a bit of an idea of the scale of this, it's a very large structure on its own. It's about 7 times the size in footprint of the Apple Cube that Lisa was showing earlier. So although, from far away it might appear to be quite transparent and quite lightweight, when you get inside the vestibule itself, it feels very heavy and very dense. And the building ownership realized this, and they knew that glass technology had improved, and in the process of going through a refurbishment of the building, they wanted this to be examined and updated. Just from a structural model perspective, this kind of shows the density. So you have a primary steel structure and intermediate aluminum framing between that, and so you get this very dense grid and relatively small panels. But that was what was available at the time, and that was as transparent as they could achieve in 1982. We were asked to re-examine this to try to make it as transparent as possible. And what we came up with were 4 initial approaches. One was to use a kind of more streamlined steel framing approach with very large glass panels, 50 foot by about 8 feet wide glass panels. The second approach was to use similar kind of configuration, just with glass framing, glass columns and glass beams that were spanning about 50 feet and glass columns that are about 20 feet tall. The third approach was to kind of utilize glass with a geometric stiffness that could span on its own. And then the fourth approach was to kind of utilize the unique conditions that the building provided, which is the fact that you have these large columns surrounding the kind of entry vestibule. And our idea was to just use the glass as efficiently as possible and just span between the columns and create a cylindrical enclosure. The ownership kind of made it clear pretty early on in the process that although it was a very efficient approach structurally, it was not an approach that was deemed possible because it deviated too much from the original architecture. So what this steel framing approach looked like, at the beginning was immediately we started just by going to these larger panel sizes, which are significantly larger than what was available 37 years ago. We're really able to kind of open up the structure, and already immediately we get this huge increase in transparency. So we established a kind of hierarchical steel structure where we had a primary steel girder that kind of split the structure in half. Again, it's a very large structure, so we found that we couldn't do it without any steel. We couldn't do it only in glass. And then we had these kind of unidirectional steel framing to kind of really open up transparency when you're walking out of the building or walking into the building looking through the vestibule itself. So this is a view looking up through that vestibule, and you can kind of see the soffit of the tower above. But really, at this vantage point, it really kind of opens up. A similar approach with the glass framing. So really just replacing the steel beams and steel columns with glass beams and glass columns. And this kind of delivered another level of transparency that, everyone, including the ownership, really thought was a promising idea. So as I mentioned, we have this steel kind of primary structure, let's say, that divides this up, and then you have 50 foot up, roughly 50-foot glass beams that are spanning, and glass panels that are, spanning between the beams. This is another view from the inside with the glass framing option. And then the third option that we did a bit more exploration on was the idea to use the glass in a geometric configuration that would help span on its own. So this kind of sawtooth pattern, which is shown here, mobilized the glass panels so that they were actually spanning on their own, and there was no traditional glass beam or glass framing that was required. And again, this really opened up the structure to be as transparent as possible. And a similar structure that was built at roughly the same period of time, 1989, so 7 years later, was the Louvre. And again, this is a structure that had the mandate of being as transparent as possible at the time. This was made very clear by the architect to the structural engineers, and we thought it was worth examining this structure with today's technology as opposed to what was achievable 30 years ago. So as I'm sure everyone here knows, this is the Louvre pyramid, and this is the primary entrance, very similar to the Philip Johnson vestibule. It's the entrance to a larger building, but obviously critically important. And what we have is a primary steel structure with glass cladding panels. And compared to what we can achieve today in size, they're again modest size compared to what we can actually achieve today. And so the first approach we looked at was saying, okay, well, what if we just spanned, one-way spanning panels the entire length of each side of the pyramid? And this is really a brute force kind of approach. Nothing too exciting from an engineering point of view. But what we landed on was a very thick assembly of glass that, as Lisa mentioned, probably isn't actually all that clear and really doesn't achieve transparency in the way we wanted to. Although it does work and is probably feasible, it would look like this, but the biggest problem is that you can't actually make panels that big, and it's not really a good idea. So we quickly deviated from that and said, okay, well, let's look at, what could we achieve with a lightweight glass structure with kind of intermediate steel framing? Could we get that to be a much more lighter and transparent structure on its own? And what we quickly realized is no matter how lightweight we make the glazing or the infill panels between the structure, the structure itself is so big that the steel framing ended up being so large just holding itself up, regardless of what kind of lightweight glass we put in, even thin glass we considered putting in. You end up with something that works, but again, is not a huge departure from the existing. So taking it one step further, we added a kind of secondary ring beam to try to break up the spans a bit more and try to get sizes to be a bit more slender. And again, what we landed on was something that, although it's, a bit smaller steel sizes, it's really not a huge departure and a huge increase in transparency. So we kind of took a step back and said, well, why don't we really, utilize the glass in a much more efficient way by making it span in both directions? So we kind of, if we can make each glass panel on its own act in two-way bending, we can actually mobilize each side of the entire pyramid as one big plate in two-way bending on its own, and that actually opened up a whole suite of possibilities. So the glass panels, in this sense, drastically decrease in thickness. What we originally kind of have landed on in its early stages were about 10 sheets of 12 millimeter, which is very thick, but these are very large panels, 20 meters, and we think could probably go down to 8 sheets of 12 mm with a bit more refinement. And the glass panels here, there's no kind of moment connections between them. There's just kind of in-plane shear being resolved and also tension and compression membrane forces. And so we get this huge increase in stiffness, a reduction in the panel thickness, and arguably a glass structure that's within fabrication limits and has no steel or backup structure required at all. And just comparing the efficiency of this two-way spanning structure with the one-way spanning structure, we see that it's given the same assembly, it's drastically stiffer than the counterpart that I showed at the very beginning. We also realized that by going to this kind of composite or combined two-way spanning plate, we really weren't limited to glass joint geometries. So we explored another geometry here, which is more of like a masonry running bond, but it's really open to a number of different options that people can explore and achieve the same results. But the big question with this is, does this achieve transparency at the level that we want, or is it worth doing this? It's a huge effort in terms of time and money and resources to go through this and really deliver a new structure. And what we aren't here to necessarily judge that. We are just asked, by people to kind of examine this and show them what is feasible and what options they have when they're looking at redesigning these things. And what's clear to us is that, we're really at the limits of what's possible in terms of glass panel sizes. We're up to 20-meter panels by 3.2 meters. Whether it goes significantly larger than that, we don't know. But it's clear from what our studies show is that, what needs a lot of work and what we would like to kind of pose as a question or a desire to everyone here who's in the industry is going towards transparent connections. So actually joining the panels together in a durable and transparent fashion is something that we think needs a lot more attention. And we can see just being here at the conference this week that there's already work being done in that, but to actually get to connections that are durable and can actually transfer large forces, that's something that we would like to kind of hopefully see be explored more in the future, because we really think that will hopefully make that transition from just the individual panels to very, very transparent structures. So that's it. So
thank you.
Thank you, Lisa. Thank you, Gregor. That was a clear call to action, and with that, I'd like to open it for a few questions from the audience, if there are any.
Hi, I was intrigued by your sawtooth idea for the California San Francisco project. Had you done the sawtooth, how would you have connected the fold lines? You're reliant on the panels kind of working compositely with each other. So a simple silicon joint presumably would not have been enough. Would it have been an embed?
Yeah, we were looking at localized embedded fittings along the length of that joint. Ultimately, that was kind of through the schematic phase, those three options, and then what was really pursued quite far, actually, was the glass framing option. But yeah, for that sawtooth option, we did have a system that was working with embedded fittings.
Not a question, but just a remark. I think you should apply that to not to the Louvre, but to Notre Dame. That's definitely the building that needs care at the moment, and it Conversely could be a good contributor to bring back UK to Europe by doing that.
Thank you for that suggestion. I think there's actually some truth on that. I had a question myself. I know that the original architect called for as much transparency as possible. You said when showing the first picture of the Louvre pyramid, you all know this site, and I think we all do. Is there a chance that the steel structure itself unintentionally has become iconic and thus has a architectural value on its own because of its recognizability?
I'm not an architect, so I'm not going to answer that. But yeah, I mean, I think it was really just an exploration in what we can kind of achieve now, and and I think where we ended is where kind of what really showed us a lot, which is that we really want to get beyond just the large panels and really start to assess how we can actually join those panels together in a transparent fashion. But yeah, I mean, it's obviously an incredibly iconic structure, and so it's special on its own, that's for sure.
It's a good thought whether you should revisit or not. And with that, I thank you for your contribution, and we'll get ready for our next few speakers in a few moments. Thank you.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!